stuff. Okay. This is like the beginning of trig, okay? I can ask you specifically about the first little part here. I can ask you if two triangles are congruent versus similar. That's about it. And then from that point forward, we're like solving problems using similarity predominantly for this lesson, okay? So we're just gonna like run through here the differences, I suppose, between similar triangles and congruent triangles, okay, which you've probably seen before, but we'll just like formalize it so that we can refer back to it. Sorry, basically, right? So congruent triangles are identical triangles, okay? So all corresponding angles and sides are equal. They're the same shape and size, okay? So here's the expression that represents that two triangles are congruent, okay? So this means that A goes with F, B goes with E, and C goes with D. Did we see what I did there? You got triangle ABC. A went with F, B went with E, C went with D. Okay, the side lines just match up, that's all. Okay? The same is true about the angles. Okay, so angle A should equal angle F. Angle B should equal angle E. And angle C should equal angle D. If we look at these triangles specifically here, you guys maybe know how to write line segments as like a formal thing that you can recognize, but here's how you would write a line segment. Line segment is created by 2 points, which we already know from our linear section. But we can call that point, or that line segment, AB. Okay? Line segment AB corresponds with, or is equal to, line segment FE. That's this one over here. Okay? And then BC is equal to ED. CA is equal to EF. Can we see what we're doing? We're just comparing side lengths, but that's how you would write a side length. The squiggly line on top? I was under the impression that meant they were congruent. The squiggly line would mean similar. Just the squiggly line would be similar. I think the squiggly with the equal implies congruent.
What's the difference between congruent and equal?
I don't think there is. They just assigned a fancy name to an equal sign. So I suppose.
The perimeter is equal or the area is equal, but the squiggly line, you want to use the area and perimeter is equal.
What she said.
But I mean, if it's an equal sign, that means everything should be equal.
Depends what you're talking about, I guess. Because this is like specifically, yeah, I guess.
It's like a similar angle where like the angle is the same, but like
the side lengths are different. Yeah, yeah.
That would be similar.
I'm not too like worried about this. This is like kind of just a formal thing, right? Because down here we're saying triangle ABC. Here's where the squiggly comes in. Is congruent to triangle FED. I'll have to look into that for you. Probably with Miss Farahani. Okay. Probably has something to do with the combination of these two things, but I can't really think of why they would be different.
Just to make it look cooler.
Make it look more mathy, scare people. Yeah. Okay, so here are your 3 conditions for congruency though. All the sides are equal relative to each other. Right? Side angle, side, 2 sides and a contained angle are equal, and then 2 angles and a side are equal. Okay? Are we okay? Yeah, well, this is like, we're just going to start applying numbers in the second half of this lesson, and that's where things actually, like, I can ask you questions. These would be like multiple choice things. Okay? So, here's what we need to prove. This isn't too crazy. We need to prove that MN, line segment MN, is equal to EF. Is it true? It's true because they've denoted here that these 2 side lengths are equal with the hash, the single hash mark. Right? So, side length MN, or NM, or MN, is equal to side length EF. Okay, that's the first one. Then we can check ML. Has to equal, I guess, FG. Okay, it's telling us that. And then we also know one other thing. What's the other thing that we see in that triangle? The what, sorry?
The right angle.
The right angle exists in both of them, so I know angle M has to equal angle F. Okay, so then if I look back at my my 3 conditions of congruency here, they might be on the, are they on one page for you? They are, aren't they? Yeah, right above. What do you see here? I see a side, an angle, and a side. So that's one of your conditions. So then these are congruent triangles. Okay? What's the next one? It looks like angle T is equal to angle G. Right? And then angle A is equal to angle O. And then it looks like, oh, we've got a shared, or the same side length too. Side length AT is equal to side length GO. So then we're like, okay, well, let's go back and look. I've got 2 angles that are the same and a side length. So that satisfies that one. So they are also congruent, yes?
In this specific situation, would it be ASA because it's angle, side, angle?
Oh yeah, specifically if you were looking here, yeah. Angle, side, angle. Red is saying, yeah,
Is that like the other ones are angle, angle, side?
yeah. Angle, side, angle. So red is just looking here. We've got an angle, a side length, and an angle on both of them. Okay? So it satisfies that. Yes? Contained is like you've got 2 side lengths like that come together. This would be the contained angle. Yeah, I suppose if they were like, they're comparing the same though between 2 triangles, so you'd have to have like another triangle with that is every angle, but we're like directly comparing 2 of them now, so they have to match up basically is what it's saying. Okay, you have a question too?
After like every question, let's say we have a question like this to prove that the triangles are congruent, do we have to determine if it's SS or SAS or AS?
To be honest with you guys, I'm not like this isn't like, this is like 4 or 5, like maybe like 4 or 5 multiple choice questions. Like this isn't like a big deal. The big thing with trig is like, can we solve problems predominantly? Yeah, right.
Is trig this year more similar triangles, or is it more like sine, cosine?
It'd be sine and cosine, tangent, and then some. It's basically, actually, what's nice about this is you guys will do this in, there's 2 separate sections of trig in the 3U course. One is this, again, almost, with a little bit extra, and then a whole new side of trig. Okay, you actually start looking at what sine and cosine are as a function on a graph. Okay, those are the 2 parts of trig in 3U. So this is all good. You're gonna see all this again too. This whole unit, yeah.
How many functions are there?
Never ending amount. There's a lot of them. Sine, cos, tan are functions. X cubed, x4, x squared, x. They're all functions. You could go x to the 100. I'm sure that looks like something. It's a function. Then you've got all the changes on those functions too, right? Like x squared plus 5. That's a new function. That does something different. You know what I mean? Relative to just x squared. You know what I mean? Every time you transform a parabola or any function, it's a new function. It does a different thing. You know what I mean?
Is this one of the harder units?
No, I would say this is probably one of the easier ones actually. This would be easier than quadratics. For the most part. Because there is a bit of a base here of things that you've already seen in grade 9. Which we'll do at the end of the day today. I think 6.2 is stuff you've seen in grade 9. Okay? That's what I was saying. Most people struggle with the quadratic section in the middle. Trig's not an issue. That's typically people do pretty well on trig. Okay? So, let's just look at the difference. We now know what congruent triangles are. Basically the exact same triangle, right? But now, we're going to look at similar triangles, okay? And if 2 triangles are congruent, there's not much we can solve for if they're the same, because they're just the same. They're not overly interesting in that sense. But similar triangles are a little bit more interesting. Okay, so let's just take a look at some of the conditions here, okay? Similar triangles have the same shape but different size overall. Okay? And one triangle is an enlargement / reduction of the other. The corresponding sides are proportional. The corresponding angles are equal. That's an important one. And then the expression is triangle ABC is similar to triangle DEF. Okay? So here's 2 triangles that would be considered similar. Okay? You can see angle A is equal to angle D. Okay? Angle B is equal to angle F. And angle C is equal to angle E.
Is it CC or?
CE? No, angles. These are all angles, sorry. I get a bit lenient on the way that they look, but they're very kind of strict.
How do you not confuse them with L's?
I don't know. There's nothing that we really use in math that would be an L.
Angle L.
Yeah, angle L. I don't know. You could say angle C. That would be common, I suppose. You could compare it. Yeah, I could see that confusion. We probably just don't use triangles with L's in them, Coco, that's all.
But like the last one we did, there was like.
Was there an L in it?
variable.
Yeah, it's like.
Oh, it wouldn't be my preferred choice of triangles, let's say. Use XYZ or ABC or something. That's not, LMN isn't really on my, I don't know, triangle favorite list. I don't know. I won't use it, Al. It's too similar, you're right. Okay, here are the conditions for similarity. You got side, side, side. So if three pairs of a corresponding triangle are proportional, not equal, then the triangles are similar. Okay, so that means, which we'll see later, that we can figure out how big they are relative to the other one using what we call a scale factor. Okay? Then side angle side, if two pairs of a corresponding sides are proportional and the contained angle are equal, then the triangles are similar. Okay? And then angle angle, if two pairs of a corresponding angles are equal, then the triangles are similar. Okay? Are we okay? No questions? Lots of words, not much action yet. Okay? Let's take a look at these things.
Is that all you have to do? Say like.
Yeah, you just look.
angles are equal?
Yeah, I mean, this is a multiple choice question. Like, this is by no means the emphasis of this unit. Okay, we just have to, like, I might say, are these two triangles similar? And you'd have to say true, false, or something, right? Or like, find the triangle that is similar to this one as a multiple choice question. 1 mark, you know what I mean? It's not the emphasis. The emphasis is actually using the fact that two triangles are similar and solving a problem. Using it. That's what the emphasis is going to be on. We're going to do some questions here in a minute. We get through this. Okay, Justice, yeah?
How many lessons are in this?
6. Did you get one? Did I put one on your desk? Okay, yeah, 6. This one's kind of 2, but like in your textbook, this is 2 separate sections here. I've pushed them into 1 unit, or one lesson. Like this lesson would be like 6-1 and 6-2. I put it into 1. Yeah, right.
You made all of these, right?
I got some of it from, well, most of it from somewhere, and then I've slowly started making it my own as I've had time to. You know what I mean? Okay. So let's do, I don't know, let's just do, yeah, okay. We can do the first one. And we'll just look at some of the conditions here, right? So, prove that the following triangles are similar. Here's what I mean by a scale factor. I'm gonna introduce the scale factor here, okay? Let's just take a look at the side lengths that we think are similar. Like these are lined up in a nice way that like it kind of makes sense. I would say that this one kind of matches up with this. Then I'd say this one kind of matches up with this. Could you tell me, like, is triangle JRS, is it smaller or bigger than triangle MEP? Smaller. How much smaller do you think? You ever hear what Retta said? It's 1.5 times smaller. How does he know it's 1.5 times smaller? Right? 9 divided by 6, 1.5. That's not good enough. Let's check this one. What's 4.5 divided by 3? It's also 1.5. This is what we call a scale factor. Okay, if you can find a consistent scale factor between the side lengths, chances are it's similar. We have one more thing to check. Do we have a shared angle in there? We do, it's right here. Then you can say these are similar triangles. Then you can use the method of solving that I'll show you in a minute. Okay? Does that make sense? Yeah, Ibrahim?
So let's say if you divide one side by the other, and it doesn't give you 1.5. So if it's like 5 divided by 3, then you don't have like common.
Yeah, this has to match.
But like, what if you get a question where it doesn't match?
That's not similar.
That's not similar, and you'd have to use a different solving method. This, I'm going to say, is your simplest of all the solving methods. If you find two triangles that are similar, this is the easiest method to solve that problem with. Okay. I can find x. How would I find x in this triangle right here? I'll highlight it. How would I find that? I just want to soak in right now. Just one sec. How would I find that? This is your precursor to what we're going to do here today. Okay.
Is it a squared plus b squared?
Yeah, you could do it that way. There's an easier way. That's a method. This is that's a method that works. But if you have a similar triangle, similar triangles are the easiest kind of trig thing that we're gonna do. Max, what do you think, buddy?
Times 13 by 1.5.
Okay, so yes, we know that these two triangles are similar. Max noticed that there's a 13 here. Well, the 13 must match up with the x, because that's the only other side length that we've got left, right? And we said that they were similar triangles. So if I take 13 and because the 13 is on the smaller triangle and this one's the bigger one, then it doesn't make sense to divide 13 by 1.5. But if I took 13 and multiplied it by 1.5, that would give me x. Okay, so what is 13 times 1.5?
19.5.
Centimeters. This is using the scale factor to solve questions.
Where did we get 13 from?
13's from the other second triangle.
Oh, it's right there.
Yeah. So then I matched up the 13 with the x because they're like shared similar side lengths, if you will. Okay. So we're kind of okay with what we're looking for with similar triangles. Okay. Why don't we just go down here and start doing some stuff? Okay, I think do you have to turn your page over? Yeah. Okay, let's go do these.
What was the most complicated?
Don't worry about those. We'll just go solve questions now. Okay. All you're looking for, Coco, is the fact that there's shared side length. You could draw both of these separately. Right? Like this one you could draw two triangles here. Draw a little one. You could label it and then draw the big one underneath. And then just talk about the fact that there is a scale factor, the angles are the same. You know what I mean? You're just gonna go through that and find, like, that's really the key, is you can draw two separate triangles and compare them. Okay, if they're contained like that, it's just a trick, right? So let's take a look at this one. Let's determine the scale factor between those two triangles. Okay, I see right off the bat, I see two angles, x and this dot. That automatically satisfies this condition, number 3, for similarity, because I see two shared two angles shared between both triangles, right? So I know I'm able to, or that the triangles are similar, right? Let's determine the scale factor that we discussed in the last question. How am I going to do that? We got to identify shared side lengths, or like similar side lengths. I see a 10.5 here, and I see a 7. What's the scale factor? What's 10.5 divided by 7?
1/3.
What is it?
1/3.
Really?
Or sorry, I don't. 1/3/2.
12, was it 12.5?
I got 1.5.
1.5.
So 3/2. I don't want to put 1/3.
Oops. Okay. That's nice. That's useful. The next part of this says here's BC. Here's triangle BC, or side length BC, sorry. It's 10 centimeters. Where's BC in the triangles? BC in the triangle. So it's going to say this side length BC is going to be 10 centimeters. Then it wants us to solve for RS. Okay? How do I find RS?
You 10 times 1.5.
Okay, so to get to a bigger triangle, I'm going to multiply. To get to the smaller triangle, I'm going to divide, because they're getting smaller versus they're getting bigger. So we have a side length on the little triangle. I need to multiply to give me RS on the big triangle. So I'm going to go 10. We'll say, hold on one sec. RS, or side length RS, is equal to 10 multiplied by 1.5, which is equal to 15 centimeters. Okay? Now, the next part here will be more meaningful to you if we actually do it versus me just telling you. So why don't we solve for the area of each of those triangles and see what happens?
Why are you laughing?
I'm just seeing if you guys are going to freak out or not.
Find the area.
Huh?
Find the area, you mean?
Yes. What's the area of a triangle? Just to get everybody started here.
The base multiplied divided by 2.
Okay, so one half area equals 1/2 the base times the height. What's going to happen here? Do you have the height of the triangle? You don't have the height of the triangle. But in theory, you could run through the proof anyway, because you know that the area is 32 centimeters squared, right? So you could go 32 is equal to 1/2. You know the base, or do you know the base? Are you stuck?
Isn't it just like QR or AB?
Well, the base in theory would be all of this. We don't know this piece, so we're stuck.
But you don't need that piece. You just need the height.
Yeah, but the base is all of that piece, is it not?
No, because the base stops there, so you just like draw a dotted line for the height.
You mean like this?
No, like I drew from S down, and that just shows the height, and then you could multiply by 10.5 and divide by 2.
I guess my point here is like, it's not as easy as just plugging it into the equation, but what should happen to the area of a similar triangle? Huh?
Should be similar to the other area.
Similar, but similar in what sense?
You multiply by 1.5.
Multiplied by 1.5. So I guess my point was like, you can run through the proof of doing it and show in this and stumble on the fact that there's a difference between the two numbers, sure. But there's something special between those two numbers, right? It should be that the area of QRS, right, should be 1.5 times bigger than the area of ABC. Because the only thing attributing to the area of a triangle is its side lengths. If the side lengths change by 1.5, then the area better change by 1.5. You know what I'm saying? So let's say the area of triangle QRS is equal to 1.5 multiplied by 32. What does that answer? is a 48. Am I right?
See, I just did the math and it doesn't change by 1.5. It doesn't seem right.
You did the math?
Like for a completely different, I made a different triangle and I did it and it wouldn't change by 1.5.
Okay, we'll have to look at it after.
Because I also did the math for like area ABC and I got 71.9848.
Not 48? What do you mean? Oh, I see. You know what it might be, Retta? I may have just made it up. I may have just said, here's the area, it's 32, and then just multiply it. I may have done that.
Is it?
I may have done that.
But even if you, I don't think if you multiply each side length by 1.5 and then multiply them, the area from
Changes?
It doesn't change by 1.5.
Okay, we'll look at it. Actually, it might not actually, you're right. We might have to look at that.
Can we just do like an example on the board?
Yeah, we'll do it after. We'll run through, we've only got these two questions here. Okay, again, this is not like, we'll look at this. Okay? Because it's worth looking at. Okay, we'll make up an example. The tricky part with this is the base piece. Okay. Let's, here's what you got going on here. So we're gonna use this idea of similar triangles to solve for a side length, okay? So on a sunny day, you're gonna have to draw me a picture and then solve the triangle, okay? So on a sunny day, Liam, who's 1.7 meters tall, right? There's Liam. He's 1.7 meters tall. He's standing by a tree, okay? He casts a shadow that's 3.5 meters long. Okay? The nearby tree casts a shadow, these aren't perfectly to scale, 18.2 meters long. Question's going to ask you, how tall is the tree?
When you do 18.2 divided by 3.5, and then the result you get from that you multiply by 1.
Yeah, so you could take the scale, like the scale factor root. I'll show you two ways to do this, Ibrahim. Okay? You can take the scale factor, which is what Ibrahim just said. We can find the fact that we can go 18.2. I'm going to a smaller triangle, so I'm going to divide by 3.5. Can everybody see where those numbers came from? 18.2 and 3.5. Okay. What's that number?
5.2.
Okay. Yeah, right. Yeah. Okay. That's just the scale factor. There's no units on that. Now, the next thing he said was, we're going to take the 5.2. If I want to figure out the question mark here, it lines up with the 1.7. So I can take 5.2 and multiply it by 1.7. That's going to give me the question mark. Okay? So, what's 5.2 times 1.7? 4.8? 8.84. That makes more sense. So the therefore, you could write a little therefore statement. Therefore, the tree is 8.84 meters tall. Okay. Now here's the other way of doing this. You can set up what we call ratios. You don't necessarily need the scale factor. So you can go, and it doesn't matter what order it is, just so that they match. You can go 3.5 over 18.2 is equal to Okay? All I did was match up the similar side lengths. Then you can do what we call cross multiplying and solve for the question mark. Right? So you'd get kind of out of room.
How do you multiply when there's nothing there?
What do you mean?
Like the question mark.
It's the question mark's just a variable. The question mark's just x. Like you're just trying to find the question mark. That gets back to x could be the smiley face or something. It's just something that you're solving for. Okay? So you can it'd be like 3.5x is equal to 1.7 times 18.2. I don't know what that is. It's a number. And then you could divide both of them by 3.5. It should equal the 8.84. Okay? You do it that way too. If you don't necessarily like setting up the scale factor and remembering, okay, I'm going from a smaller one to a bigger one, so I have to multiply, or just that step of having to remember something, if you just want to set up a ratio and then cross multiply and solve, it's all good. That'll take care of it for you too. Okay? Okay, let's take a look at this question. You guys can probably see this a little better on your sheet because I lightened the picture off. Okay, but basically what you got going on here is Chelsea's trying to measure the width of a river, and she marked out the following diagram. Okay, how wide is the river? Okay, so you could draw the two triangles, that's fine. So basically what you're going to have is you're going to have something like this. It's a little hard to tell with the 3D picture. It's because it is kind of 3D. You're going to get a picture that looks like this, two triangles, right? One's going to be 3.2, one of the side lengths, and the other one's going to be 7.5. Okay, and then the big one, the one that's actually going across the river, it'll look something like this.
Did you get 7.5?
That's back here in the picture. Can you see it?
Oh,
Is it in your picture?
yeah.
It's notoriously a bad picture. Like it just is what it is. I tried to lighten it off before I photocopied it. Can you guys see it? Okay. So 7.5 comes from there. And then the bottom of the big triangle is going to be 17.3. And then X is going to represent this piece here, the actual width of the river. Okay. So you could do one of two things here. You could find the scale factor between these two pieces, right? And then know that because you're going from the small one, you could multiply this value by the scale factor to give you X, right? Because you're going from a smaller triangle to a bigger one. Or you could set this up. Okay. Cross multiply. 3.2x is equal to 17.3 times 7.5. Divide both sides by 3.2. Cancel, so x is equal to, has anybody done that?
You also do the factor.
I can do the scale factor one too if you want, yeah. In a sec here, we'll just make sure the numbers work. I got more space with this question in here. What do we got? 17.3 times 7.5 divided by 3.2 should get 40.5 meters. Okay. If you wanted to do the scale factor way, you know that the one on the right's bigger, so you could go, okay, well, what's my scale factor? Well, we could go 17.3 divided by 3.2. That's going to give me a number, specifically 55.36. That's your scale factor. Then you could take that, you know you have to multiply to get from the smaller one to the bigger one. So you're gonna take 7.5.
17.35 by 2.2 is a 55.
What is it? Sorry, what did I do?
5.4.
Sorry, I must have typed it in wrong. I would have caught that, and you guys would have caught that too when you get a number astronomically bigger than 40.35, because then it doesn't make any sense. It's a lot for me to like type in things. That's why I ask you guys to type it in too. It's 5.4. Okay, there's your scale factor, sorry. And then we can go 7.5 multiplied by 5.4. Which should equal 40.5. Two different methods. I would think one has less thinking involved than the other. The only thinking that's going on here is remembering, am I going from the big one to the small one versus the small one to the big one, right? Okay, I think the area has to change. I think red is right, just because of you're multiplying the side lengths together. So we'll check that in a sec here, okay? You guys, there's homework questions on the board there, okay, for this section. You can give those a go, okay? Well, while I sort out this area thing, okay? Yes, Justice? Oh, you're early today. Thank you. I gotta plug it in. We're through the period though. I don't need it anymore. Okay. I'll sort out this area thing. Okay.